Hey there, this is Dafer, and you're watching the Fourier Automation channel. Most of my videos are aimed at making technology more accessible for hobbyists, serious students, or even professionals that are trying to make a break into robotics or aerospace. And this is no exception. Today, I want to walk you through a great project that's quick and easy to do now, and will get you started programming a tiny microprocessor using bare metal programming. In this video, we'll be targeting the Texas Instruments MSP430 microcontroller. The designation microcontroller means that it is a entire computer all in one chip. This is it right here on this evaluation board. It has ROM and RAM memory. It has ports for peripherals and, of course, a microprocessor. It comes in a variety of different packages and evaluation boards. Here are several. This is my favorite, this adorable little USB fob that has this detachable MSP430 microcontroller on board in the back here. I've soldered some pin headers here, female, onto the board. This is another variation that has Bluetooth and other RF capabilities, antennas on board. This again detaches. So after you're done programming it, you can then attach it to some other device or embed it in another device. But today we'll be targeting the MSP430 Launchpad, which is this one right here. To program the device, we'll be using Code Composer Studio, which is a free download from Texas Instruments. And the reason I'm redoing this video after many years is because in recent years, Code Composer has become much more easier to use and available, and the entire tool chain of programming and the limitations on the free version have become so liberalized that and easy to use that it's really a no-brainer now to just install Code Composer Studio and program and plug in your MSP430 into a USB port and start programming. It's that easy nowadays. It wasn't in the past, which is why I've held off on this. I'll put a link in the description below for where you can download Code Composer Studio. And after you're done with that, I suggest you pause the video. When you're done installing that, come back and we'll get started. So the topics I want to cover in this demo today are pulse width modulation and using hardware interrupts. Again, we're doing some bare metal programming today. Let's start with hardware interrupts because that is fundamental to doing pulse width modulation. Now, we're going to be doing pulse width modulation in a very bare bones way, but you don't have to because the MSP430 has several ports on it that will convert an analog signal to a pulse width modulation. So you don't have to worry about that if you don't want to, but you can use hardware interrupts to create pulse width modulation. So starting with hardware interrupts, let's get this concept laid out. There are at least two ways to get the state of a peripheral device like a magnetometer or a button press or something like that. One is by polling that device, and the other is by using hardware interrupts. Here are two real-world examples of each. Let's say you've rented a cabin in the Rocky Mountains and you want to bake your favorite cookies while you're camping there, but you only have a primitive wood-fired stove, no precise temperature control. And also because you're 10,000 feet at altitude, all the baking instructions, including the time, go out the window. So there's no point in even using a clock or timer because you don't know how long it's going to take to bake your cookies. The best you can do is start with your cookie recipe and estimate the amount of time that it usually takes at sea level. And then after that, every few minutes, go back to the stove, take a peek at the cookies. They're not ready yet. Go watch some more birds. Come back in another minute or two, check them again. And you keep doing this repeatedly until you visually observe that those cookies are done baking. What you've done there is you're visually polling your cookie's state. And that gives you an idea of what polling is. In programming, if you are polling a device, you have to be in a loop. You have to be running a loop. And one of the instructions in that loop checks the state of the device. It queries the device for its state. Is this button pressed down? There's problems with that. One is that in a device like the MSP430, you're sort of wasting power. If power may be scarce, because the device has the capability to go into a low power or a sleep mode. And if you are running a loop perpetually, in some contexts, you're wasting power. The other problem with that is that depending on what you are doing in your main loop, while you're waiting to poll once again, you may be, while you're processing other commands, you may be missing a button press that happens quickly in between polling events. So someone may be pressing a button, but you're not seeing it because when you poll the buttons, the person has already lifted their finger from the button, and that event is not recorded. That's polling. On the other hand, using hardware interrupts can be very advantageous in certain contexts. Now, what does that mean? A hardware interrupt is a memory location on the board, and it's managed by the hardware so that when something like a button press or a peripheral state changes, the state of a button changes, or the state of some other device, a sensor, changes, it signals using that hardware interrupt memory location, and the microprocessor itself knows to check that memory location intermittently or at some high frequency. And so wherever you are in your processing stack, even if you're asleep and saving power in some low power mode or a sleep mode, that hardware interrupt will wake up the microprocessor and will interrupt the execution stack of the microprocessor. And then you've already assigned an interrupt handler routine to the hardware. When that happens, it will call that interrupt handling routine. And that may do whatever you want to do when that state is achieved on the peripheral device. So there's no need to be looping. There's no need to even be processing anything. Alternatively, you may have a very large set of routines that you are looping through perpetually, and there's no need to coordinate. You're not polling anymore. You're relying on the hardware interrupt. Wherever you are in that execution stack, the hardware interrupt will interrupt that execution, execute your interrupt handler routine, and then return to where you were in that execution stack. So that's what we're going to be doing today. Now let's talk about pulse width modulation. Pulse width modulation is a solution to the problem of ports like these that are digital. It means they're binary. They can only be on or off. There's no partial output of voltage. And so, and output or input. On a digital port, pulse width modulation allows us to simulate a partial signal, partial voltage, or a percentage on or off. And this is extremely useful, especially in things like RC planes and cars and boats, and pretty much anything that requires an analog output. So let's start with a real world example. Let's say you have a light in your dining room that can only be on or off. There's no dimmer. Okay. So you flip a switch and it's on, and you flip the switch down and it's off. How can you simulate 50 or 80% luminosity? Well, conventional light bulbs, traditional light bulbs, incandescent bulbs, their response on a micro level, their response to being on or off is very slow. The filament inside that bulb will continue to glow and gradually, if we're talking about in the span of a second or a half a second, that glow will continue. So if you flip that switch on and off fast enough, the human eye may not observe a change in the state of that bulb, but we may observe that the bulb is giving us not its full luminosity. Now, the human eye can only detect changes, in a 20th or a 30th of a second. A microprocessor like this it has a frequency of, between several hundred hertz cycles per second, up to 25,000 clock cycles per second. So if we have a port here, this LED, for example, if we were to flip that on and off at 1,000 hertz, 1,000 cycles per second, then the human eye would never observe any flicker. But depending on how much of that cycle is on and how much is off, we may observe a reduction, a static reduction in the luminosity of that LED. So for example, and I'm going to throw up some charts here on the screen. Let's say we have a period or a frequency that we're flickering that port on and off is 100 times per second. And 50% of the time it's on, 50% of the time it's off. What we're going to observe in that LED is about 50% power. If we, for example, have, it's called the duty cycle, how long it's on, per the frequency. Um, so if we have it on 90% of the time and it's only off 10% of the time, what we're going to observe is something like the 90% power luminosity of that LED. So the amount of time for each cycle of the frequency that it's on is called the duty cycle. So how do we accomplish pulse width modulation? Well, as I said, these um, these microcontrollers, almost all of them have a clock on board, and that clock uh, is linked to one of the hardware interrupts in the microcontroller, in the microprocessor. So after a certain number of ticks of the clock, which is running at 25,000 cycles per second, um, you are going to tell it to turn on this port. And then after another different number of ticks, I mean, you would turn it off. And this is something that you would do in the background if you're going to do it at all. If you're not going to rely on the microcontroller evaluation board to do this for you, the ports, if you're implementing this yourself, you would do this in the background with a prearranged routines. But today, what we're going to do is use a different hardware interrupt to catch this button press. There's a button right here. And what that's going to do is change our duty cycle and change the luminosity of the LED on the board. Okay, let's go through the code and let's run it and step into it. I am not going to cover how to make a project in Code Composer Studio today. There's plenty of videos on YouTube that can help you do that. I will put links in the description for that, and also for where to download my code that you're looking at right now in Code Composer. So first let's take a look at this code. This is our main routine. We are stopping the watchdog up here. We are enabling the hardware interrupt on port 3. We are setting the output, we're setting port 6 to output mode, and we're setting the period of the pulse width modulation here. We're setting the duty cycle to 50 initially. Our button presses are going to change the duty cycle, and you'll see that in a minute. But I want to call attention to this part here. Right here, we are putting the processor in low power mode 1, which will still deal with an interrupt, hardware interrupt signal. Now, any code after that, I've put a comment here to explain this. Any code after that will not execute. So if I were to continue writing lines of code down below this line, anything below this line will not execute because the microprocessor is essentially sleeping. However, this is our interrupt handler code, this block, okay? This block will get called with each button click twice two times, one for the down click and one for the up click. Now we have to handle counting whether it's you know, an odd number of clicks or an even number of clicks. So we only want to react when it's the up click, the second click. So we're going to ignore every other click or every first click. So this is our interrupt handler routine. Now let's put a breakpoint. Well, first I'm going to run the code, and you'll see that it always breaks at the first line of the main routine. So it's broken here at the main routine, the first line. So I'm going to go ahead and I am going to just have it proceed with no breakpoints, and you're going to see what it does. So here's our LED that we're looking at right here. Right now it's at 50% power or 50% duty cycle. When I press this button, it will increase the duty cycle. I hope you can see it getting brighter. Now it's gone off. With each click, it gets brighter until it shuts off. And then it starts the cycle again. Now, if I put a breakpoint in the main routine, it's not going to hit it. However, if I put a breakpoint here in the interrupt handler routine, you'll see that it breaks. And each time I do that, I have to hit continue to see the result of that click. When I hold it down, it doesn't break in that spot. When I lift it up, it breaks. So that shows you that the interrupt handler, let's put a breakpoint up in the main method here. See that it's, I can't put any breakpoints there because it's never going to hit it. So that demonstrates that the interrupt handler routine is being called with each click of the button, and this if clause here is being entered with each up click of the button. So that's it. So I hope this was helpful. I hope that's clear. If not, feel free to ask me questions in the comments, or if you find anything that I said wrong, you can do that too. Thanks for tuning in. I hope you found this demo useful. And I'll put links to where to install Code Composer, and I will put links also to where to download my program in the description below. Thanks for tuning in. Have a great day.